Hi, can you hear me? Yeah. Yeah. Just turn it on. Yes, it's your green. Good day, or in Swedish, or good afternoon, everybody. I have the enormous pleasure. Thomas is in charge of the colloquium, but he gave me the pleasure to present Andreas Isacsson, a colleague of mine when I go to Sweden. We fika a lot. For you that don't understand what it means, fika means we drink a lot of coffee. We spend a lot chatting, and he's the professor in charge of the class that I teach there, because technically I'm not associated there, so he's in charge of that. So we have a long history in the last 4 or 5 years, probably, since this Linnaeus-Paume program started between UNAM and the University of Gothenburg. Now here comes the part. He is a professor, let me introduce it properly. He's a professor of the University of Chalmers, which are together. It's more or less the same as UAM and the UNAM here. The two campuses that are shared, and they are together. So Professor Andreas Isacsson was born in 1975. He's a professor at the Department of Physics at Chalmers University of Technology in Gothenburg, Sweden. He received his PhD in physics in 2002 from Chalmers under the supervision of M. Johnson and R. Schechter, studying the theory of nano-electromechanical systems in single electron systems and superconducting devices. Between 2003 and 2006, he worked as a postdoc fellow at Yale University and at Nordita in Copenhagen, focusing on quantum phase transitions in ultra-cold gases and frustrated spin systems. After this, he returned to Chalmers, and he is now a professor at the Division of Condensed Matter and Material Theory. Here, his main research interest is in nanoelectromechanical systems using low-dimensional materials such as carbon nanotubes and graphene. And more recently, he's working on wetting phenomena involving 2D materials. Apart from research, he has also keen interest in teaching and is currently the head of the physics bachelor program at Gothenburg University. And that's our connection. He's in charge of assigning all the classes and stuff at the Gothenburg University. And in the Gothenburg jargon, I am known as a kind of superhero, but he's Robin. I will not tell you which superhero, but he's my Robin. And he's now doing that in the class on complex variables. So, Professor Andreas, welcome.
Thank you very much,
Amy. Talk. Today we will listen to elasto-capillarity in the nanoscale, the physics of wetting induced deformation, and he has a test for us.
Yeah.
Thank you.
I have a quiz for all of you. And this is the first time he will actually learn about my research, despite all that we have talked about. So I'm very pleased to be here. And well, the talk you have already seen, elasto-capillarity on the nanoscale. And this is something that came up because 2, 3 years ago, I became interested in a very complex topic, and that is phase transitions in suspensions of graphene oxide. They can have, you get liquid crystals. And I wanted to investigate this. So, and we started, and you start always simple. Let's make some simple tests just to see that the simplest possible system we can look at. And then we got a bit confused, so we looked at something even simpler. And then we got even more confused. So then we looked at the simplest possible thing we could look at. And this is what I will talk about today, because we discover things. So where will I end up today? So I will begin with showing you my last slide, right? This is my last slide. And by the time we come to the end of the talk, you will know what I'm talking about, hopefully. And the person who is behind this is my postdoc, Martha Cutter, who has been working with me now for the past 2 years. But first, what is elasto-capillarity? It's deformation induced by capillary forces. And this is everyday phenomenon. Actually, almost all of you every day experience this. Now, Remy was very nice, kind, and allowed me to get one of his favorite red folders to destroy. Okay, I've cut it apart. It's still possible to use a little bit. But if I take this guy, Just put it together like this, it goes apart. Okay, I put it in water. And now when I take it together, what happens? Yeah, it sticks together. How long have you known this? Ah, you knew it, right? When your hair gets wet, it sticks together, right? But sometimes it's the things we see every day and don't really think about, that when we ask the question, we find nice physics. So if you knew this in 2007, you could have written a physical review letter on this very topic. And if you were thinking even more, you could get a science paper if you took a very, very thin film, it's 180 nanometers thick, and you put this floating on water, and then you put a small water droplet on it, and then you study the wrinkling pattern. Then you could publish it in Science. Something that's very important here in both of these, and I will come back to this, but I want you to remember it. It's the scale here. This is 0.5 millimeters, and this is 1 millimeter. Remember those numbers. Now, what can you use it for? When this 2007 paper came with the wrapping of the little thing, they also played with some other things, which is called capillary origami. And it's self-assembly, essentially, using capillary forces. So what they did is that they took this little actually, do I have something some stick to point with? I can use this one, but it's very hard for the camera. Oh, if you have one. Okay, never mind otherwise. Continue. Okay, never mind. You have perfect. Okay, perfect. Yeah. So here again, I would like to point out the length scale, 1 millimeter, 1 millimeter, and they cut a little triangle of a very bendable material, and you put a water droplet, and it folds up to this little pyramid here, tetrahedron. Or you make something that looks like a flower, and it also folds up into a closed shape. And then you can think about using this for like micro-fabrication of very complicated 3D structures. So here is the same example. Now we're down to 100 microns. Now this is a metal structure where you have used actually molten metal on top to make it fold into a very, very small cube. So again, the size scales. But this is a problem that has really old roots. This is not modern physics. This is super old physics, and that's why it's so fun. It starts out with Jacob Bernoulli in 1654, and then with his nephew, Daniel Bernoulli. And of course, Euler is involved in this. And then there is an important person here, that's Laplace, because he will be bridging two things without realizing what he's missing out on. And of course, Young, the polymath. Gauss is involved a little bit also in all this story. And then Maxwell. And then my favorite physicist, who is Rayleigh. He enters the story everywhere, because whenever someone writes an article, you will find a comment by Rayleigh in another article saying, actually, it's like this. So what did Bernoulli do? No, it's good that I got the stick. So he asked a simple question. If I have a very flexible stick, I will not break this one. And I have a weight here. It will bend if it's a very flexible stick. What shape will it take? Yeah, simple enough problem. He works on this for a few years. And he comes up with a solution, right? So you really needed to be good with your drawings at that time. I do not pretend I understand how I got the solution, but the important thing is what it says here. Curva elastica. This is the shape. And this is taken from, it's a very nice, it's not published, but you can find it on the internet, the Elastic Mathematical History. And then there are a lot of famous people involved discussing this. Both his nephew, but there is Leibniz saying you should not really work on this problem because it's too complicated. You will not be able to solve it. But then Euler comes along. So this is 1694, and then we go to 1774. It's a long time that's passing. And what Euler does is, of course, he has just thinking about in terms of variational calculus. So he says that suppose I have, now you can imagine that I have this thing, and suppose I only deform it in one dimension, so I don't do any twisting. And then it says, suppose it goes from point A to point B. And then I know the tangents of these two. What shape will it have? And then what you have to do is that you have to minimize a functional. So the energy is proportional to the radius of curvature square. So we should minimize that energy. And if you parameterize, so the curvature is really just the circle that makes the tangent here, the radius of that circle. And if we express it in terms of a radius vector that goes along the curve as we are changing s, it looks like that. Now, there is an important thing we should add to this part. And that is that in the theory of the Euler Elastica, this guy is conceded as we cannot stretch it. And that means that if we really want to do this minimization, it's very convenient to impose a constraint. So if you're ever doing exercises in variational calculus, I suggest you to try this problem, because what you do, if it has a size L naught, I will use the same notation later, so I made a little paper. It has a width and a length, right? And I want to constrain my S to also have the same length. Then we introduce this Lagrange multiplier here. So this is an elastic functional that we should minimize to get the shape. Now, fast forward another, what, 130 years, okay? Someone wrote a entire PhD thesis on this. And it's a physicist. Does anyone know who got their PhD in 1906 and could possibly have worked with this? This was Max Born. So he did his PhD thesis studying solutions to the Elastica, but also in 3 dimensions. And of course, the dashed line here, in what I showed you before, that is, of course, an Elastica curve. But there is something else where the Elastica shows up, and that is actually Laplace. He noticed that if I have 2 plates, narrow plates, and I have a capillary rising between them, the shape of the meniscus can take the shape of an Elastica. And it was, well, Maxwell points this out. So what is it? Then here is one of the most interesting things, and that's the history behind capillarity. So this was observed by many, but it's like a mystery. We learn about this in school, right? Capillary rise. And then you ask why? Capillary forces, right? Capillary forces. But they didn't know. So at this point, we didn't know about atoms or molecules, but they assumed there were particles. They were called particles or molecules or atoms. But you needed to have all these guys, Laplace and Young, who were the oldest here, they started out, they made this assumption. There are particles and molecules because they wanted to understand surface tension. They understood that these forces had something to do with surface tension. And that must involve some kind of force between particles. They don't know what a force is, but they make an assumption that's amazing, that it's a force that sort of acts over a certain distance, but then falls off. And they are even able to estimate it, the correct order, sort of order of magnitude up to some angstrom or so. But then they also need another assumption. And that is the fact that think of it, this is an attractive force. But why doesn't everything just go into a big ball? So Laplace introduces what he calls, there is some kind of pressure holding it outwards. Today we are talking about Laplace pressure. Today we know better about kinetic theory and so on, but they didn't really know the concepts of pressure, surface tension, cohesion. Kinetic gas theory comes later, like in 1850s, so it comes a bit later. But how do we calculate the rise? Well, we need to know three things. We need to know the surface tension, and we need, which is actually the free energy density, the energy per area that the water does with the vapor phase. And then there is a corresponding free energy between the solid, the tube, and the liquid, and an energy associated with the solid and the vapor. So you can think of these as surface tensions. But if you want to know the total free energy, is quite easy. You can set it up. It's just the center of mass of the water to a certain height here. And then as we climb up, it's just the area around the tube where we have water. And then we get changed by the difference of these surface free energies. Minimizing this, we get the Euler equation. If you look at this in many textbooks, it is done very complicated with forces and pressures and whatnot. And what Young did here is they sort of thought of all these as surface forces. So this is the Young-Dupré equation for wetting angles. You think of this as a surface tension, and then you say there is some kind of surface tension here and here as well. Today we think more of these as free energies, and then we don't have to think about the forces. If we assume that we have a spherical droplet, then in most articles on this, you find the following statement. We should minimize the free energy, which is the surface free energy times the area of the liquid vapor interface, and the difference in free energies between solid vapor and solid liquid. And then comes this term. And it's very weird because the V squares as radius to the power 3 and the area is to the radius power 2. So of course I minimize this by taking the radius to infinity. Now what this is actually a Lagrange multiplier. The P is a Lagrange multiplier saying that we should have a constant volume. An alternative is to say, and we will do molecular dynamics soon, is to say we have a certain number of molecules in the liquid and a certain number of molecules outside. So we put our entire system in a box, right? And then this guy actually has a minimum, because now we can find a thermal equilibrium with minimizing the shape of the water. And then all we have to do is to use that we have our equation of states. Now we see that this Lagrange multiplier is the pressure. And we retrieve the Young-Dupré equation and the equation for the Laplace pressure. So the pressure inside a droplet, it decreases with the size of the droplet. Okay, if you want to read Young's paper, it ends very nicely. Yeah? Okay, so here I'm assuming that I actually don't have any exchange of particles between across the faces. Otherwise, we have to introduce the chemical potentials also in this problem. Yeah, we are calculating. So we are actually saying later that okay, oh, you could have it in another. You could have the water and you could have some other gas, but we will do this in vacuums. We will not bother about this term. Maybe I should do like Thomas Young and claim that I will publish something that will contain a clear and simple explanation of the most important parts of natural philosophy. Little did he know about quantum mechanics to come. Yes. Now, length scales. I told you about the millimeters, right? So that's a water droplet of length L. It's a fluid, it has on density and surface tension. And it's going to sit on some material which has some elastic parameter, a Young modulus or bending rigidity. And then we have nature. So when a drop falls down, there is a gravity force acting on it. So it goes as L to the power 3 at the volume. But that means the pressure it exerts on the surface well, then I should divide that force by L square. That force goes as rho GL. On the other hand, the pressure inside the droplet, that goes as 1 over L. And if you set these equal, you end up at the critical length scales for water that is a capillary length. So when we have a droplet that's smaller than like 3 or 4 millimeters, then capillary forces dominate over gravitational forces. So this is why in the experiments they were so small. Now, we can also create another length scale. And that's the elasto-capillary length scale. So that has to do with the Young's modulus. If I put a droplet on top of a substrate, of course, there will be forces from the droplet on the substrate, so it forms a little wetting ridge. Now, the size of that wetting ridge is of the order of surface tension over elastic modulus. So it's insanely small for most materials. And it's only very recently within biophysics and so on, able to see this. But if I have a membrane, it has a bending rigidity, B, and I can form yet another length scale, B square root B over gamma. And now I have another inequality. If L is larger than this guy, I can start deforming the membrane with capillary forces. And of course, I have to satisfy this inequality, because otherwise the bending rigidity is too large. But I still have to be smaller than this guy. So, oh, time is flying. Now the guys who published in Science, of course, they could use the same experiment in Physical Review Letters again. But now they were discussing, when I have this droplet on top of the film, what is actually the wetting angle? Now, on the scale they are doing it, it looks like essentially the bending rigidity is 0. So it just forms a very sharp kink here. Now, 2 years later, there is another experiment, Schulman and colleagues. They do the same, but they have a film and they actually have droplets both on top and below. And they are also studying the wetting angles. The reason to have it below is to show that gravity doesn't play any role here. And Scholl and colleagues, they say that, okay, this angle plus this angle is approximately the wetting angle of a flat substrate. Now, these guys, they say, not really, it's almost, but it depends on the tension in my membrane. So there is a correction. It's a little bit vague, the reasoning behind it in the paper, but it works. It agrees with the experiment. So now there is something very recent. It was on the archive like a year ago, but it was actually published 1.5 months ago. As a paper on how to model this. And what they do is they consider a water cylinder. Water cylinders are not very common, but they are good for models to understand what happens. And they say, if we look very closely here, then actually, if we take the tangent here, we do have the wetting angle as it should be. What they are measuring in the experiments is they are zooming out here. And when they are zooming out, they are looking at the angle between that one and that one. So locally, the wetting angle doesn't change. This is a very debated topic in the literature, these wetting angles. But they also do something else. And now we're coming close to the diagram I showed you in the beginning. They say that the shape of this membrane depends only on 3 parameters. You can make 3-dimensionless combinations. You have the wetting angle for the flat membrane. You have the tension in the membrane divided by the surface tension of the water. And then you have a combination of the surface tension, the cross-sectional area, and the bending rigidity. And if you choose one value of this combination and a wetting angle, you can measure the angle beta here as function of tension. And what you see, if you have high tension, it doesn't deform much. You go down, and eventually you are forming like a complete vesicle like this. And if we do it in the variational way, well, we start out as before. We have now 2 parts of the free energy. We have the elastic part and the part for the water. The part for the water is the same as before, except we have now an area up here. W is the width of this guy. So we have the area of the interface, let's say the vacuum. And then we have the area where the water is in contact with the membrane. And then we have the free energy of the water inside. And then we have the elastic energy. So now we do the thing that now we minimize all of it together to get some equations. And this is what Kozyrev and colleagues did, and actually it was done earlier by Neukirch and others, but it's a little bit confusing paper because they involve gravity. We get out the Young-Dupré equation. Sum of this angle and an angle that I haven't drawn here is the Young angle, and we get the Laplace pressure for a cylindrical one. And we get what is known the pressurized Euler-Elastic equation. And we also get all the boundary conditions coming out that ensures that we have force balance at this triple phase contact line. But it's still a macroscopic theory. There are no molecules in here yet. So can we do this with what happens when we go down to the molecular level that Laplace and Young and so on were talking about? They were talking about forces between molecules. So when graphene came around, the single layer of carbon, people started doing a lot of things with this. You could get publications. Just have graphene in the title and you get a good publication. That was the mantra. So Patra and colleagues made a molecular dynamic simulations. They put about 17,000 at the most water molecules on top of a small piece of graphene and simulated for up to 1 nanosecond. And what you see are 2 droplets. And actually what they are doing is one of them is ever so slightly deforming the membrane and creating a little pit for it to sit in. But the one on the other side, it will sit in the next pit. But we're also having graphene, the long-range van der Waals forces, they go all the way across the membrane. And it's called wetting transparency. And then they try, okay, we can simulate this origami with a 2 nanometer droplet. And we can make things roll up. There's nothing quantitative in this. It's just fun stuff, right? But these 2D materials are then extremely flexible. The bending rigidity of graphene is like 2 electron volts. And if the surface tension of water is 70 millinewton per meter, we get this elasto-capillary length is 2 nanometer. It's enough with a 2 nanometer droplet to bend things, to bend graphene. But there is a problem. It's not really 2 electron volts because graphene is all the time flopping like this to thermal fluctuations. And we know that this is easy to bend, but once I do this, it gets harder to bend. It's easy to bend on a very small scale, but hard on a large scale. So it also depends on the radius of curvature where you try to bend it. And this is Misha Katznelson. He has worked many years with this, and he has actually borrowed things from tethered polymer membranes by David Nelson on theory. So what do these thermal fluctuations do when we wet it with like this 2 nanometer droplet? This is a study that came in Nature Materials in 2016. So this is 1 nanometer, and you see on top a graphene membrane, 15 by 15 nanometer, and the blue areas, there it is buckled downwards. The red areas, it's buckled upwards, and the green areas are somewhere in between. And let's look at this one. With time, 0 picoseconds, 120 picoseconds, 240 picoseconds, thermal fluctuations change where it's buckled up and down, and the droplet moves. And they were able to get this very nice, what they call surfing. So here, it is actually not the water that is deforming the main mechanism. It's rather the fact that the thermal fluctuations for such a small droplet are so large that they will cause the dynamics of the droplet. But this is molecular dynamics. I always give, whenever you see molecular dynamics, be very skeptical because it's always wrong. It's never entirely correct. There is good molecular dynamics. There is sort of okay and there is outright wrong. The important is, what is the question you're asking? Is that possible to answer by the molecular dynamics? And the wetting angle of graphene, that's very elusive. People are still publishing on this. This is from 2018. Graphene is hydrophilic with a contact angle of 42 degrees plus minus 7 degrees. This is an experimental paper. Experimental paper from 2022. There's a water droplet sitting on graphene. It's definitely not hydrophilic. There are numerous MD calculations on flat graphene. And the thing is, if you want in your paper, in your calculation to have a certain wetting angle, you can basically search the literature until you find a reference that has that wetting angle. Because people still don't know. So we do not pretend to have the right wetting angle, and it is not important. So what do? We want to go to something bigger. We can't have the two small droplets. We want to approach this continuum. So instead of typically 10,000 or 17,000 molecules, we use 150,000. And instead of simulating for like 1 nanosecond, these systems can take a very long time to relax. So we have to simulate for up to 30 nanoseconds or more sometimes. And we have to use, we want sizes that are much larger, so up to 200 by 50 nanometers. Some details, and this means that we have to use a lot of core. You can't simulate it on your laptop. This is like calculations that have taken well over 1 million core hours to do. And what this is a snapshot of one of our MD simulations. So we are not showing the individual atoms. We are showing the graphene membrane. So this is after approximately 20 nanoseconds. We are simulating this wide membrane, and we have a periodic boundary condition in this direction, so we can get a stable cylinder. And this is to be able to compare with continuum theory and avoid effects of what's called contact line curvature. So this droplet is now 24 nanometers. And we see that it has really, really deformed it, and we have applied a tension. And this tension has to be, of course, of the same order and lower than the surface tension for us to really see anything. And now we are interested in, does this wetting angle thing, well, really, this was a test experiment to see if our simulations worked. We wanted to compare it to this continuum theory that was very recent, and it turns out we couldn't, no matter how hard we tried. But it's large enough for stability. So does it work with this continuum theory? Yeah. So this is one of the samples. It is also molecular dynamics simulations. You see the density contours. 10 times the surface tension. If I stretch it with that, well, the membrane is virtually flat. If it's the same as the surface tension, it goes very smoothly. We get these very nice shapes. And we have very low tensions. What happens is that this becomes very noisy because we are at 300 Kelvin. And if you want to simulate something like this, it will slowly start flopping like this. So you will have very slow modes in this that go around. So it doesn't really, we should see, you are not seeing the entire ribbon. You are seeing a small part of it. So the entire ribbon, we want to simulate something that the theory works well if it's an infinite ribbon, because then we can solve it. So this is a 200 nanometer long ribbon, I think. But you are only seeing something like maybe 40 nanometers here. You're not seeing the very, very long tails. So qualitatively, it's correct, except that when we go to 0 here, it folds up upon itself. And that's because we have van der Waals forces between the graphene layers. So it forms like almost this onion. But that works fine. The wetting angle. That's also a big thing. How do we need to know what the wetting angle is? So usually when you have a small droplet, this is, I think, 2 nanometers, we benchmark to some other paper on a flat surface. You have all these density contours, and then the question is, where is the surface of the water? And the usual but there are different ways of doing it, but often you take it where you have half the density or something like this, and you have to time average, follow the center of mass. And for small droplets that are circular, you have to correct for contact line curvature. Now we are using large droplets. This is our 24 nanometer droplet, and that is like a cylinder that is 15 nanometers wide. So then we see it doesn't really matter if we are going at high. We do have a very sharp surface, so we can fit this. We actually, to fit the angle, it's actually better to use the yellow one, which is a slightly elliptic fit, but it's never perfectly circular when we do this. So it always moves around. And then we determine, using a fitting algorithm for all our samples that we have simulated for different tensions, this angle beta, the lateral, and this angle theta d. And this gives us the wetting angle as function of tension. And now, does it agree with continuum theory? So now there's a lot of things in this graph, so let me go slowly. On this axis, it's a logarithmic scale. So this is the tension in the membrane divided by the surface tension. So here it's really high. On this side, I have two different angles. I have the wetting angle, theta y, and I have the angle beta. So theta y is this angle, and the beta is this angle. Now, the black dots, these are the angles beta from all our simulations. So down here, at very, very high tensions, it's flat. We go down, and eventually we make this transition to a vesicle. Very close to the vesicle transition, it's extremely noisy, because whenever you have a transition, you have noise. And the blue guys here, the dots, those are our measured wetting angles, but they do not stay constant. They change, and we can actually see it with our bare eye when we look at our simulation, that these are no longer constant. Then we can compare it with continuum theory. So this purple line is the continuum theory, assuming that bending rigidity would be 0. And it fits qualitatively well, it's right order of magnitudes. Then we can take the continuum theory that using the elastica and everything, when we get the red curve. If we allow to change the wetting angle, so now what the black curve here is we use the continuum theory, but we say, okay, let's use theta y as a parameter and try to fit these guys. Then we actually end up with a variable wetting angle that does quite well with our simulations. So we are actually fitting two curves with one parameter. This is very important. It's not like we are fitting both of them. Now, to get this curve, you can argue that, but I mean, there are parameters going into this. What if you have the wrong numbers? And this is what you have in molecular dynamics, right? So we need the bending rigidity. So how do we do that? We simulated all our ribbons without water, just pushing them together like this at 300 Kelvin. And then we fitted to the Elastica solution at finite temperatures. And the important thing with this is that then we catch the renormalization due to all the thermal fluctuations. And we get it at the relevant radii of curvature. And depending on, and we get values, we'll get a good fit, but between 2.5 for the smaller ones and 3.5 for the larger ones. But this angle beta that was a curve, it depends on 3 parameters. The tension we have control over in our simulation. The wetting angle, well, we can measure it with our model. And then there was this mysterious parameter gamma. The wetting angle, the surface tension is tricky. So in order to make sure, at first we try to fit our data to the theory. So we really pushed at what parameters is the really, really lowest we can go so we can get it as close as possible. What is the largest margin of error we have? And for that, we found out that the lowest, I mean, typically you get from the water model we use, you should get something around 60, 70 something, 60, 63 with a water model. But it turns out that some guys found that if you use a special type of long-range solver we use, it may be lower, but it's certainly not lower than this. So this is a lower bound. So we tried that first. Maybe that's the error we make, but it wasn't. The other one is, okay, let's really do this and see our bending rigidity. Maybe it's much stiffer than we thought. So we really push to the upper bound to get a lower bound on this, because the lower this one is, the more we can shift our curve down. But still we cannot shift it down. We would have to change by a factor of 10 to get agreement with the data. And now I come back to the first slide. So what we did was that we looked at, can we get to the continuum by doing very large scale MD? So all of this is MD. This is where we see the molecules, and here we have just processed the density and taken a contour of a density contour. So this is also MD data. And then we mapped it onto the continuum model and said, okay, we have to make some kind of changes in how we define the wetting angle here. And currently we have some ideas. Of course, we are looking at a region which is not actually a point of contact. This has a size which is of order of the range of our van der Waals forces. And we also have continuous thermal fluctuations going on in this system. And of course, when it's this small here, using macroscopic thermodynamic parameters like pressure and so on, it's not really well defined anymore. But we were still surprised to see how well it actually fitted this simple model, but we see some deviations. And now that we are done with this part, now we sort of realize that our very big ambitious project, it will have a lot of other paths before we are there, because there's a lot of things here that are not understood. And for that, I would like to thank you for your attention.
Thank you very much for this nice combination of classical, old, new physics. Questions? Yeah, Sebastian? There are no stupid questions.